welcome to today's IWCS. My name is Connie, and I'll be your Cisco WebEx producer for today's event. Now, I am pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box in the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Asher Novick, optical engineer, Panduit Corporation in Illinois and United States, who will be presenting his paper on correlation OTDR for accurate measurements of optical length of fiber optic cables under diverse environmental temperatures. Asher Novick is currently an optical engineer in the Fiber Research Department at Panduit Laboratories, Panduit Corporation. Asher received his Master's in Engineering and BS in Electrical and Computer Engineering from Cornell University in Ithaca, New York in 2016 and 2015, respectively. His research experience is in biomedical imaging and optical communications. Asher, we welcome you to present at today's IWCS webinar series event.
Okay. Hi, everyone. Just wanted to acknowledge that for some people it's a Good Friday or the first day of Passover, so thank you for joining, especially. So I presented this paper in October at IWCS in Providence, and it's about correlation OTDR to really, really accurately measure optical length of fiber optic cables. And before we get into it, I just want to quickly define the difference between cable length and optical length of the fiber optics. So the cable length is what you measure out when the cable's running through. It's the physical length, whereas optical length is the actual path length of the light as it travels through the fibers. They're similar, but not exactly the same, and that is important. So this was work from our labs. That's me, Asher Novick, Jose Castro, Rick Pimpinella, Bülent Kose, Paul Hong, Fei Jia, and Brett Lin. So there's this big demand for tight length tolerance in fiber optic structured cabling. Previously, it was the cable and fiber costs, because people didn't really want to have the waste. But now there's different economic factors. Very critically, things like high frequency trading, where length equalizing different lanes is especially critical. The paper was actually kind of spawned from a customer request where we were requested to provide 12 and 24 fiber cables that were within a 0.25% of the length specification for all the fibers in that cable. So they didn't so there was a specification, and it could be, for this cable was 100 meters, these 10 cables were 160 meters, et cetera. And so all the fibers had to be within a 0.25% length of one another. So if it's 100 meters, they couldn't vary by more than 25 centimeters. And they couldn't vary from the specification or each other by more than that. And the reason why is applications like high frequency trading is that a length difference creates a signal difference, time of arrival difference, and it's unfair if one lane is getting preferential treatment, i.e. it's shorter, so their signals get there sooner. And when you're talking like we're talking like nanos. I think light travels about a dozen or so centimeters through a fiber in about a nanosecond, and so that's why these specifications have to be so tight. There is just one example of this already being a big deal, is just the round trip between the Chicago and New York Stock Exchange. Basically, someone in 2010 paid hundreds of millions of dollars to shave off the round trip time for data by 1.4 milliseconds, and they made their money back quite quickly just from leasing lanes on the fiber of this tunnel. They dug it as straight as possible, just to trading firms. They made everything back quite quickly. And now there's also these microwave, which is they can go straighter than any tunnel, but there are other issues with the free space propagation. But the point is, just even shaving a millisecond off of something like the Chicago to New York Stock Exchange round trip is a huge deal worth many millions of dollars. So one of the issues we ran into when we were trying to fulfill this customer request was a lot of the commercial OTDRs, they come with the technical specification that they can measure something like plus minus 40 centimeters. And that's kind of a problem when we need something specified to plus minus 25 centimeters or even better. So we in the Fiber Research Lab came up with another solution. So typically with like a traditional OTDR is you can have a very narrow pulse, which will give you better resolution but might not go out as far, and that's figure 1A, and figure B is the OTDR trace where you have the reflections as it goes, or you have a wider pulse, figure 1C, and it goes out. It can go out farther, but it has less resolution. So what we did instead, because that didn't give us quite the resolution we wanted, we replaced the wide pulse with actually a sequence, like a repeating sequence, and instead of just simply measuring time of flight, and dividing by 2 and then multiplying by the speed of light, we sent a sequence and did a cross correlation with a reference sequence and the sequence that we sent. And the sequence doesn't you can optimize it for different things, but the point is, by having this, it's not just a single pulse. By having all that, it's almost data, and correlating, you get a much higher resolution. And we actually tested this. Well, so one of the way we validated it was we actually kind of laid out a fiber under test on the ground and measured it, got some measurement within a couple millimeters, and then put a ruler down next to it, and, cleaved off 2 millimeters, measured again, and, we could see that the measurement was now 2 millimeters shorter. So that was just one of the ways we confirmed the trip. That we confirmed the test. So just going back to mechanical versus optical length. These were 3 different cables that we had our manufacturing group create. And so one cable was almost 38 meters in mechanical cut length. That's what the spooling machine read out. One was 161.4 meters in mechanical length, and one was like 167.6-ish. And what we did was each of these cables has multiple fibers in it, and we then measured the optical length using this correlation OTDR of a couple of fibers in each cable. And you can see on the y-axis here, due to a number of factors, including index of refraction, changes the speed of light in the fiber, and also just they take different physical paths. The fibers, they don't necessarily go straight through; they might wrap around a core. So we saw almost up to 0.7 meters length difference between the fiber optical length and mechanical cut cable length. So if you're trying to provide for very tight specification just by your mechanical cable cut length, 72, like it's already 3 times higher than the allowable error, and that will create issues in trip time on like several nanoseconds, and that's just not acceptable. And then even among, and so it's not just mechanical cut versus optical length. This graph actually shows that there in a 24 fiber MPO terminated multimode fiber cable that was 50 meters in length approximately. We found that this is the optical length of each of those 24 fibers, and that's basically 2 ribbons. And between the 2 ribbons, within one cable, within one 24 fiber cable, we found up to half a meter length difference. So that was kind of just the importance of being able to measure with this precision. So this is roughly the experimental setup for what we're doing. We have a control PC, an arbitrary waveform generator. The evaluation board uses a so another really important part of this is that you can get things that will measure optical length to millimeter precision. Those products do exist, but the ones that I'm aware of don't use the application wavelength. Or so I know of ones that are in the visible spectrum and one that's out at 1550 nanometers. But if you want to get an accurate length measurement for a multimode fiber, like it's not necessarily like published what the index of refraction is of an OM4 fiber at 1550. It is at 850. So if you can use 850 nanometers, you know what, not just, you're using the right index of refraction, but you actually have the length that the application is going to be seeing. So it's just a little bit higher confidence. So with our evaluation board, when measuring multimode fiber cables, we could use a multimode transceiver. So the optical length we're seeing is the same optical length that the real data signals will be seeing in the application. And vice versa with a single mode. We just use a single mode transceiver. And so that went into a splitter, went out into our fiber under test, the DUT. For this paper, we put that fiber in a thermotron chamber just so we could record how the optical length of the fiber changed with temperature, which was varied between minus 40 Celsius and plus 100. And then at the end of the fiber, it bounced back from the termination, come back in through the splitter into the receiver and back to an oscilloscope. And so we have, the AWG is putting out, the arbitrary waveform generator is putting out a trigger and also a reference electrical pattern. And then the PC captures the reference pattern that's the same as what's driving the evaluation board, and also the detected pattern coming back from the fiber, and then does a cross correlation between the two to figure out length. So what we found was that it was the hotter the fiber got, the longer the optical length was. And so, for example, at room temperature, so this is with a 46-meter optical fiber. So at room temperature, 23 Celsius, we measured the fiber at 46.44, lowering it to 10 Celsius. It dropped 2 centimeters in length. Minus 40 Celsius, it actually dropped a whole, from the room temperature, it dropped a whole 13 centimeters, and then going up to 75 Celsius, it actually gained a couple of centimeters. And this was with a jacketed optical fiber. The next slide is we put a bare spooled optical fiber, and very similar. It was a little more responsive to the higher temperatures. What was interesting was at the very highest, at the 75 Celsius temperature, you can kind of see on the next slide, it'll show more. There was this almost an overshoot, and then the fiber length settled. So we haven't looked into that more yet, but we do intend to, just because it looks like an interesting effect. But when you plot the temperature versus optical length, you can see it's a pretty straightforward relationship. Like I said, there were some differences between the jacketed and the bare fiber behavior, but for the jacketed to a polynomial fit, it was R squared of 0.99, and for the bare fiber, the linear fit was also very, very good fit. So just to conclude, there is this really large demand for very specifically specified in terms of length optical structure cabling, and you can't just use the mechanical length of the cable that from the manufacturing floor. You really need to verify the optical length within the cable. There are a bunch of different factors, like the difference between mechanical and optical length, like the difference between the optical length of the fibers within the cable, especially when you have like something like a 12-fiber ribbon or a 24-fiber cable that has two ribbons. There could be a pretty significant difference between the optical length within there, which could be more than 25 centimeters, which would be the spec for an 100-meter for this specific request. And there's also this strong dependence on, or a very highly correlated dependence of the optical length on environmental temperature. And for that, there was actually some, fortunately, it was observed that once going back to room temperature, even though there was this really strong dependence where the length would change depending on temperature, when it went back to room temperature, it would go back to the original measurement. So there shouldn't be any real concerns, at least within the range we tested, so like minus 40 Celsius to plus 75. If you want to store cables, when they're being stored, the optical length would be different, but once they're installed, they should come back to the original length. And then this correlation OTDR, which is the other real focus of this paper, really, really consistently and with a good degree of confidence measured the lengths really precisely. We didn't have any issues. It was a quick measurement and very consistent, and like I mentioned earlier, we were able to validate it just by, with a ruler, we could, snip off 1 or 2 millimeters of fiber and immediately see that the measurement measured 1 or 2 millimeters shorter. So that was really cool. I think I spoke a little quickly, but that is the talk. Thanks for listening, and I believe Ed is going to be handling questions.
Yes, thank you, Asher. At this time, we will ask as many questions from the attendees as time permits, starting with this first question. Are 5G or applications such as driver-assisted cars, virtually instantaneous round-trip data, also incentives for tight length tolerances?
So my current perspective on the necessity of tight length tolerance is having a relative length tolerance between parallel fibers. But I could definitely, so for example, with things like high frequency trading where you need equalized paths, but I could see future applications where you need where you need to know the exact latency you'll be dealing with to a sub-nanosecond scale, and if you needed to know the latency that your application will see to a sub-nanosecond scale, this would be a good tool to use in that situation.
Great, thank you. Next, has the internal design of optical fiber cable geometry, fiber configuration, changed to accommodate reduced round-trip data time?
So that's an interesting question. I was having a conversation with someone relatively recently, and I believe that there are certain so when you have like an OM4 or an OS2 fiber, it's not going to be specifically designed for latency. The multimode will probably be more designed for bandwidth and band radius type things. But I believe that for issues with latency, there are fibers with a reduced refractive index core, so light will travel a little faster through them. But they're more for pretty specific applications, as far as I'm aware. But there are definitely solutions to of like non-typical fibers to reduce round-trip data time, I think.
Okay, thank you. Next, what does real installation temperature change or cycling have on round-trip data time?
So I guess I'm not 100% sure, but they're definitely in data centers. Equipment heats up. That's a major energy is used to cool them down. So I would think temperature could have an effect on the fiber that's like adjacent to maybe a server that's getting a little warm. But I don't think it would, because only the adjacent length of that fiber would be affected, and I would expect that no specific length of fiber is going to be. So for this test, we put the whole spool in the oven. So unless the entire building gets up to 75 Celsius or minus 40 Celsius, I don't think it would be a critical issue. But it is nice to know that if you were to store it at in like a freezer, you could take it out, and once it reached room temperature, it would be the original measured room temperature length.
Okay, thank you. Next, are there cable designs that best equalize the optical length of individual fibers?
I'm not sure. That is something that I'd really like to test. I know that there are some new, just from IWCS last year, there was a lot of talks on different cable designs. I haven't tested that, but that is, yeah, I'd like to test that.
Okay, great. Next, are the differences noted in your length attributed to actual contraction of the fiber material, or is it more attributed to changes in the IOR with temperature changes?
So that is another question that I very much would like to know the answer to as well. I personally, my theory that I haven't been able to test too much yet is that it's more a mechanical stress thing, especially with the difference between bare fiber and jacketed at the higher temperatures. I think because so when you put any sort of mechanical stress on a fiber with you can see in the speckle pattern on a multimode fiber or the polarization on a single mode fiber, you do affect the optical path going through. And so as things like the coating or the jacketing, as they expand or contract with temperature, I think they're putting a stress on the outside of the cable, of the fiber where the light is propagating. I think that is causing an effect on the optical path, similar to if you were to touch it with your finger. I think there's more than one factor, and I haven't had a chance to narrow it down.
Okay, thank you. At this time, I am seeing no further questions. So I would like to thank you, Asher, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Asher after today's event. Each of these IWCS series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, May 17th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 67 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, September 29th through Wednesday, October 2nd, 2019, at the Charlotte Convention Center in Charlotte, North Carolina, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 17th through Thursday, March 19th, 2020, at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.